All right. So we are wrapping up the vectors portion of the course right now. So yesterday we started this lesson, cross product and its properties. So you can watch, hopefully you've either watched the video or you will go back and watch the video to get the nitty-gritty pieces of information of how it works. There's a geometric cross product and an algebraic cross product. But the key idea to recognize is that when you apply the cross product to two vectors, you get a vector. Okay? The cross product of two vectors is a vector. So the geometric definition is magnitude of vector u times magnitude of vector v sine theta. That's a scalar without just that bit, times by n hat. When you see the hat, remember on a vector, it means that the vector is a unit vector. And the n is symbolizing normal. So normal is a way of indicating perpendicular to both of the given vectors. So if you look at my picture up here, this is my perspective drawing version of it, that says if u and v lie on a horizontal plane, the vector that would be perpendicular to both would be vertical. Okay? Another way of thinking of it, if you want to think of the red and the green, okay, it's more like saying that the red vector would be coming out of the board, and the green vector would be going into the board. If you think of the u and v being on the smartboard flat or on your page flat, coming out of the board, going into the board would be basically your perpendicular vector. So you can only calculate the cross product in 3 dimensions. There's no such thing as a cross product in 2 dimensions. Okay? So we learned also the fact that the direction of the vector depends on the order on which you put the cross. So if you have u crossed with v, you take your right hand, you line your right hand up with your vector, the first vector, in this case u, and you want your fingers to curl towards vector v. So if I line up my right hand with vector u, my pinky would be lying along vector u, and because my fingers are curling towards vector v, look at where my thumb is pointing, guys. It's coming out of the board or out of the page. And then if I wanted to do v cross u, do you guys see my hand has to change orientation here because to curl towards u from v, you guys see that my fingers, in order for my fingers to curl, I have to line up my index finger with the vector curl and my thumb's going into the board. So the order of the cross product matters, so it's not commutative. Okay? We then did a geometric analysis, the fact that the magnitude of the cross product is actually equal to the area of a parallelogram. That ends up being one application of cross product. You can calculate the area of a parallelogram. If you know the two vectors and the angle between, you can calculate it this way. Okay? Then there was the algebraic definition of the cross product. This is a memorization game, guys. You have to learn it. It will not be provided. Okay? The cross product formula is as follows. You have two vectors, a1, a2, a3, and b1, b2, b3. Then the cross product is this combination of the numbers. a2, b3 minus a3, b2. a3, b1 minus a1, b3. a1, b2 minus a2, b1. How are you going to remember it? It's numeric. First of all, it goes in order of first vector, second vector, a, b, a, so it's that order. And then the numbers in the first part always go up, and the numbers in the second part always go down. So it's 2, 3, 3, 2. And then the next one starts where you left off here. 3, I can't go up anymore, so I have to go back to 1. 3, 1, 1, 3. Okay, and then 1, 2, 2, 1. Okay, so that's the order. There's a memory device that if you want to draw, the way the memory device works is if you write down A2, A3, A1, A2, and B1, B2, B3, B1, B2. It's, again, you basically can create the pattern by starting here and crisscrossing your way down like a zipper almost. So it's like A2 matches up with B3. There's my first combo. Subtract A3, B2. So there's your first cross. So A2, B3 minus A3, B2. And then start the next cross. A3 crosses with B1, A3, B1 minus A1, B3. Yep. And then last but not least, A1, B2 minus A2, B1. We good? So it's a memorization device. You just have to learn it. because you will be asked to apply that on the assignment. On the assignment, you can just refer to the formula, but on the exam, you will be asked to calculate cross product at some point. It will happen. Okay? So we did here. These were the geometric ones. So again, watch yesterday's video to go through in depth how we got these. And then we did an algebraic one. Again, it just becomes a plug and chug into the formula. Okay? I don't need to see, do you guys see this line? I showed it to really break it down into the piece by piece, but I'm okay if you go right to the second line where you already do the multiplying in your head. Just be careful. Okay? And once you find this vector that's the cross product, in part B, what we did was we confirmed that that vector was orthogonal. Orthogonal is just a synonym for perpendicular. Perpendicular to the original two vectors by using the dot product. Remember, dot product is a perpendicular checker. So if I know that if I want to check to see if two vectors are perpendicular, if I find their dot product is 0, then I know that they're perpendicular. So this is a proof, or this is a check to make sure that the vector I found was actually perpendicular to the first two. And that's where we left off. So we're on to C. So determine vector A crossed with vector B plus C and vector A cross B plus vector A cross vector C. What do you notice? Question. So we're going to do, we're going to do this numerically and see if we notice that there's a pattern or not. So we're going to start with A crossed with vector B plus vector C. So vector A is 7, 1, negative 2. And in brackets, we're going to add vectors B and C. So vector B was 4, 3, 6. And vector C, sorry, back first slide. Vector C was negative 1, 2, 4. Okay. So order of operations would say you should do what first here? Add the vectors in the bracket. So we got 7, 1, negative 2 crossed with, the way I add vectors in 3 dimensions is I just add the corresponding coordinates. 4 plus negative 1. 3. 3 plus 2. 5, 6 plus 4. 10. And then now I'm going to do the cross product. So this is where you may want to do, it's up to you, like you want to go just to name it for something here, A1, A2, A3. Now I don't have to call it, like technically this is not really B. You want to pick a dummy variable, K1, K2, K3, or do you want to stick with B's and just remember it's not really the B's? Yeah, sure. Okay, B1, B2, B3. Okay, it's not really the vector B. This is just a memory device. Okay, so again, when I start the cross product, the first thing I start with is 2. Okay, so I'm going to start with A2 times B3. 1 times 10 is 10. Minus A3 B2. Negative 2 times 5 is negative 10. So something to get in the habit of doing, automatically put the minus and then adjust it if your next product is negative. Does that make sense, guys? So I wrote A2 B3 was 1 times 10 is 10. I write the minus sign, and now I'm doing A3 B2. Negative 2 times 5 is negative 10, which means I'm actually going to add 10. Now I'm going to do A3 B1. Negative 2 times 3, negative 6, minus A1 B3. 7 times 10 is 70. And then A1 B2, 7 times 5, 35, minus A2 B1, 1 times 3 is 3. And I get the vector 20, negative 76, 32. Okay? Now we're going to evaluate the second expression, and we'll see whether or not we get 20, negative 76, 32. If we do, what operation is true then if we see A cross of a sum is A cross first plus A cross second? It means distributive property is a property of cross product. We get 20, negative 76, 32. So we're going to do it. So A cross B plus A cross vector A cross with vector C. So again, we've got 7, 1, negative 2 crossed with 4, 3, 6 plus 7, 1, negative 2 crossed with negative 1, 2, 4. So we have to do cross product twice this time. Okay. So again, maybe we'll just go 1, 2, 3, 1, 2, 3. And like, if you may not need to do this, it's up to you. Okay. So A2, B3, so the first number in this bracket is A2, B3. A2 is 1, B3 is 6. 1 times 6 is 6. I write my minus sign. A3, B2. Negative 2 times 3 plus 6. Okay. A3, B1. Negative 2 times 4. Negative 8 minus A1, B3. 7 times 6. 42. A1, B2, 7 times 3, 21, minus A2, B1, 1 times 4 is 4. I ran out of space. Shouldn't have done that.
Just shrink it. Can't you shrink it?
Yeah, just group it first. Doesn't want to group. Okay, now it's not. Now I'm not moving it. Okay, my little numbers. Okay, so.
Another practice.
Okay, so I'm just going to do this, guys. Plus, this is what if you run out of room, you can just kind of, you should never end, this is just for you for the future, guys, you should never end a line of your solution with an operation. Just start the next part, that would continuation with an operation. So I'm going to start with the plus. Now I'm going to do these two. So A2, B3, so 1 times 4 is 4. Minus A3, B2, negative 2 times 2 is negative 4, so that's a plus 4. A3, B1, negative 2 times negative 1 is 2, minus A1, B3, 7 times 4, 28. A1, B2, 7 times 2, 14, minus A2, B1, 1 times negative 1 will be plus 1. So I end up with 12, negative 50, 17, plus 8, negative 26, 15. And lo and behold, if you add those vectors, 12 plus 8 is 20. Negative 50 minus 26 is 17 plus 15 is. Hello, Miss, it's here. It's here. Cool. So that's how. So what do we notice? Question mark. The vectors are the same. Distributive property exists if possible. Okay? So you're allowed to do distributive property with cross product. Now, technically it would be a stronger proof if I made you do this algebraically. It's a bit of a nightmare. Do you get why it's a bit of a nightmare? Because now the vectors aren't numerical. It's A1, A2, A3, B1, B2, B3, C1, C2, C3, and now you have to deal with, then you basically have this expression, and then you have to add another expression to it, and you have like A1s and B1s and C1s all being added, and A2s and B2s. It's doable. It is possible. You might be asked to do that as a proof next year. Okay, but moral of story for us is these are the properties of cross product. So as we've built our way through the last 2 units, any operation we've learned with vectors, we had to discuss what the properties were. So commutative property does not exist. An adjusted commutative property does, where if you change the order, you have to change the sign. So U cross V is equal to negative V cross U. Because if that's going to be the opposite direction, if I multiply by negative, it'll be the same direction, they would be equivalent. The next 2 lines, guys, these are your distributive. It's just a matter of saying, is it cross, like if you have U cross V plus W or U plus V cross W, either way, you're basically doing distributive property. Okay? Now, the second last point here is kind of a cool rule here. It says if vector U and vector V are non-zero, And the cross product of the vectors is going to equal the 0 vector if and only if there is a scalar m element reals such that the vector u equals m times vector v. So you know how the dot product, if the dot product is the value 0, you know the two vectors were perpendicular. If the cross product is the 0 vector, it's telling you that the vectors are scalar multiples of each other. So remember we said there'll be a fast way to check to see if vectors are scalar multiples, instead of you having to go through each and adjust and see how are they related. Now you have a way of figuring it out by just taking the cross product, and if you get 0, 0, 0, it means that they were scalar multiples. Okay? And then last but not least, there's a point there, it's very rarely used, but just again, just to understand that you have a scalar multiple of a cross product. You could scalar multiple just the first vector and then do the cross product, or you could scalar multiple the last vector and then do the cross product. You get the equivalent answer every time. Properties of cross product. So now, hello, Miss. Yes. Okay, just 1 second, guys. So let's start this question off. Determine the area of the parallelogram defined by these two vectors. So I now am telling you find area of parallelogram. What did we say at the beginning? The area of a parallelogram, that's horrible parallelogram, okay? Area of parallelogram is magnitude of cross product. Okay, if you go back to the first definition of the cross product, this came up. Parallelogram's area is if I just want the area, it's not the vector part, it's just the magnitude of the cross product. You have your vectors here, guys. Can we figure out what the cross product is and then take the magnitude of it? I'm going to press pause and I'll let you guys get going on that. So, I gave you a bit of a head start here. So we had 4, 5, 2 crossed with 3, 2, 7. Right?
You have to show that stuff?
No.
Oh.
You just go right into numbers, it's fine. So A2B3 minus A3B2, A3B1 minus A1B3, A1B2 minus A2B1.
Oh shoot, minus.
See, it's tricky, right? You gotta be careful.
I'm not gonna give him
Huh?
Miss, you have to make a song for that now. Yeah. 0, that's
I don't know if I can make a fun cross product song.
No.
Can I make a what?
Cross product.
Ow!
Okay. Sorry guys, I don't have my calculator.
Nice mental math.
Okay.
Oh, I'm kidding.
49's the last one.
31.
I feel like 1494 seems to ring a bell.
Now don't trust me.
The third time I've done this literally today, so I think I got it. Okay.
Miss, why did you put the song? Yeah.
Yeah.
It's the fun night.
Okay. Moving on. All right. So we got root 1494. Guess what? It's an area. I'm gonna go flashback to AP Calc, guys.
Oh, I thought you were going to say
Integrate it. No. You never have to integrate again until next year.
Oh my god, that's so true.
All right. Now, find the angle between vectors u and v. So, find the angle between vectors u and v. Have we found angles between vectors before?
Yes.
We sure have. But we could do dot product. We could totally do dot product. But you also you just found that the magnitude of the cross product is this number. Isn't there a geometric version of cross product that you could equate to root 1494? You could do So if I know that the magnitude of the cross product is the square root of 1494, doesn't that mean that the magnitude of u times the magnitude of v sine theta is equal to root 1494? Is it easy enough to find magnitude of u and magnitude of v? From last week, guys, if I want to find the magnitude of a vector in 3 dimensions, triple Pythagorean.
Yep.
So vector u was 452. So 4 squared plus 5 squared plus 2 squared. Vector v was 327. 3 squared plus 2 squared plus 7 squared. So we end up with
My ears are so distinct.
What? I just said that.
with the tail on the u.
did? Yeah.
I can't now because we're doing like the U in between, you know, like union or whatever it stands for. It's not union. But anyway.
I think that one's root 45.
Plus 25.
Hello. Yeah.
All right, let me just. All right, so
What's the second one, guys? Root 62. Okay.
Come on.
So root 45 times root 62 sine theta is root 1494. Sine theta. You guys get it just a number crunch now?
In that case, can you just go straight to zero?
Yeah. If you want right to theta, it's fine. Okay, so
Don't be lazy, Luca.
I do lazy, but yeah, laziness is fine.
it works? Okay. Oh, okay. Okay.
21 and 4.
Okay, perfect. Okay. So, root 1494 over root 45, root 62, I think you got 47 degrees if my memory serves me.
Yeah, I think that's correct.
I hope my memory serves me on the exam.
Okay. Do you just have to memorize all the answers in your head? Okay.
But if you give us the answers, I'll make it up.
It's gotta be.
You know what? I think I'm going to pass.
Sounds like a challenge.
What they do?
Challenge denied. Okay,
No.
last part of the course, guys. We're 9 slides away, or 10 slides away. 10 slides away. Okay. So, what's left to do? Now that we know the cross product, we're growing to love it, I can tell. Crickets, okay? So we're going to now apply it and dot product to real life situations. Now you might be saying, hey, the dot product we already did applications for. We did applications of dot product in 2 dimensions, but sometimes we have to use the dot product in 3 dimensions. So the first scenario we're going to look at is something called torque. Okay? Torque is a measure of the force acting on an object that causes it to rotate. So you use torque anytime you use a wrench, a screwdriver, an Allen key, you're screwing in a light bulb, like any of these things, you're applying a force horizontally or rotationally to cause something to go in a perpendicular direction. Does that make sense? You're turning a screwdriver because you want the screw to go into the wood, but you're actually moving it like perpendicular to the way it's actually going in. So that's torque. Okay? Torque is an application of cross product. So it's the cross product of the force and the torque arm, where the torque arm is the vector from the pivot point to the point where the force acts. There's going to be a picture on the next page and I'll show you what I mean. The formula for torque is capital T vector, torque, equals torque arm crossed with force. Typically this becomes, well, I'll leave it like that. So that's your formula. Again, if you wanted to write it in terms of geometric, it would be magnitude of vector r times magnitude of vector f, sine theta then technically times by n hat, right? Technically that would be the torque. The times by n hat is just your stand-in for we know the vector needs to be perpendicular to these vectors and go in a certain direction. Usually in real life, we're not going to go angles and things. We're going to say out of object into object. Okay? So here's an example with a wrench. A wrench is used to tighten a bolt. A force of 60 newtons is applied in a clockwise direction at 80 degrees to the handle, 20 centimeters from the center of the bolt. Calculate the magnitude of the torque. So, do you guys see the forces, or the force at work here? This is literally how you would apply the force, right? Your arm would be here, and you'd be pushing at the end of the wrench, right? So your force is doing this. What happens is you have this wrench that's a certain length. The longer it is, the more torque you're going to get, because you have a longer pivot arm. How many of you guys get to use the IKEA Allen key that comes with your thing? It's like that an Allen key is one of these little tiny L-shaped metal things. And you use it to spin, you're putting together your desk, or you're putting together a table, and it's throw this in, and then you're supposed to spin it to tighten it, and then you put the screws in on the other side and all that kind of stuff, right? So an Allen key has a tiny arm. That's why it doesn't take a lot of force to spin it around, right? You're not dealing with heavy forces. Whereas if I want to tighten a bolt and I want it to be on a pipe, and I don't want it to ever move ever, and I'm super serious, I'm going to use a wrench that's going to have a little bit longer torque arms, because you can get more force to force that bolt to be tighter, right? It's hard to you can only do so much with this little Allen key. If you have a longer torque arm, you're going to have a little bit more room to apply a force, if that makes sense. Okay, so we want to calculate the magnitude of the torque. So first of all, this is, as soon as you see magnitude of torque, life is beautiful. You don't have to worry about the n vector, n hat. You don't have to worry about it. Just magnitude of torque. The magnitude of the torque is the magnitude of the torque arm vector times the force vector, which becomes magnitude of torque arm vector times magnitude of force. And for cross product, which ratio are we working with, guys? Sine theta. I don't need the n hat because it's the magnitude. Now, when you look at the picture, do you guys see that it's not oriented where the vectors are tail to tail, right? So can I make the vectors tail to tail though, guys? Could I transfer the force vector? Fine. Okay. It's gonna be, I don't know. Okay. Sure, sir. Okay. Yeah. Okay. Yeah. Okay. Sounds good. So anyway, so we're gonna work with this expression here. Okay. Magnitude of a vector r times magnitude of force vector sine theta. Can I reorient my vector here? So here's this vector that's kind of hanging out over here. Can I orient it so it's tail to tail with the other vector? Take a look, guys. Does that make sense? Okay. And so technically, the 80-degree angle that's here, you guys see that it's also here? Z pattern? Okay. So the angle that the force made with the wrench here is the same angle that the wrench makes with the bolt, if that makes sense. Okay, and then, so now we're going to just we literally have everything we need. Now, the one thing you have to be careful about when we do this is the units for torque are Newton meters. The units for torque are Newton meters. So, I can't use 20 centimeters for the magnitude of vector r. What should I use instead? Yeah, 0.20 meters needs to be used. So it's 0.20 times 60 sine 80 degrees. Okay, let's see, memory 11.4.
Okay.
Yeah. Yeah. Is it 11.8? Sorry. 11.8 Newton meters. Now, just so you guys know, I don't really know why this textbook decides that it works in joules, but this is in Newton meters, because technically this could also be in joules. A Newton meter is a joule, okay? So I don't know why they decide to leave it in Newton meters. I'll take either, okay? So now, in what direction does the torque vector point? So basically, is the torque vector pointing into the, like wherever you're tightening this bolt, let's say we're tightening a bolt so it goes into an object. Is the torque vector going into the object or out of the object? So take a look, because we reoriented our vectors tail to tail, and it's vector R is first, so you would align your arm with vector R. Do you guys get that? In order to align it with your right hand with vector R, I would line it up actually here, right? Like this. So your wrist needs to be where the vectors meet. So maybe I'll be clear about that. Your wrist needs to be where the vectors meet. Okay? And so do you guys get, if I'm curling from the torque arm to the force, does everyone see me curling? So I'm curling like clockwise. Do you guys see that the bolt, look where my thumb's pointing, the bolt's going into the board. So this is tightening. We knew it was tightening anyway. It was a little bit of a guideline there. So we know the bolts, the torque vector is going into the board. Okay? The torque vector.
If it was on the other side, then it would be going out, right?
Right. And this is why, let's say board / object, whatever, okay? Page. This is where you get the idea of, I'm sure you might have heard this before, lefty loosey, righty tighty.
Yeah.
Okay? So because I'm rotating right, like clockwise, i.e. with the right, I'm putting something tighter, so righty tighty. But then if I decided to put the force the other way, it would loosen, and the torque vector would mean the bolt's coming out. Mm-hmm.
I don't know if you know the answer, but what if it's like a left-hand thread? Because then the torque will still be in that direction, but it's going down. So.
Well, then you'd have to be spinning. If it was the other way around.
Yeah, and if it was like this, then it would be loosening. So how does that work in general? I mean, maybe it's a question.
Yeah, I don't know.
Okay.
It's not going to give you like the one weird. It's a different type of screw or something. This will be the rule. Okay, it's basically apply it, and there you go. So that's the rule for that one. Okay, and then moving along, just when you thought you were done with vector projections, okay, we're going to do a projection of a vector onto another vector in 3 dimensions. So again, I would go into, remember my little the symbols here we use, projection of V onto U. What's the tiny vector? What's the subscript vector going to be? U. Okay? Now, let's see if we remember this. The formula for the vector projection is dot product of 2 vectors on top. That's easy. Dot product of the 2 vectors, U dot V. Now, the rest of the expression is all going to be with the same vector. Which one is it? Are we going to have lots of U's or lots of V's? Because we want our vector to go in the direction of vector U, so we have to relate it all to the vector U. So the vector V, whatever's big here only shows up once here, whatever's tiny here shows up everywhere else. So we've got that magnitude of vector U squared times vector U. Remember, this came from the idea that you're really doing this right here, right? This is your scalar projection, and you're timesing it by a unit vector in the direction of vector U. This is where that formula came from, right? This piece is the scalar projection, okay? And this part's, you times it by a vector in 1 unit long, then you get your vector projection, okay? But in order to do this, I just need to plug and chug some numbers. I have the vectors. Can I find the dot product? Can I find the magnitude of U? Yes and yes. So I want to find the dot product of U and V. 4, 2, 7, dotted with 6, 3, 8. So at this point, once you get the hang of dot product, I'm okay with you just doing the multiplication in your head. 4 times 6, 24, plus 2 times 3, 6, plus 7 times 8, 56. 56 and 24 is 80, so, or 86. Yeah? Okay. And then I also need, what other numerical piece do I need to fill in over here? Magnitude of u, which is our triple Pythagorean. So it's vector u, 6 squared plus 3 squared plus 8 squared. So technically I did something a little bit bad here. I switched to big D and U from our commutative. It doesn't really matter, but technically I should have put like this here and this here because it doesn't really match the line above. But what do I get here? 36 and 9, 45, 45 plus 64. 109, I think. So I go back over here. Can I turn everything into, can I go into numerical mode over here? The numerator becomes 86. The denominator is magnitude of u squared, so it's just going to be 109. And then vector u is 638. Then we're just going to distribute that lovely fraction to all three parts, and we're good. So we're going to have 86 times 6. Need some help, guys. I was going to go run and get my calculator.
516.
86 times 6 is 516. 3 times 86, 258. And 8 times 86, it's 688. Okay. Yay, vector projection found. I also want the magnitude. I could go one of two routes. Okay, I could do just to find the magnitude of this. Doable, it's kind of yucky, but you can't. Or you could go back to finding this. Which technically, if you want to find the scalar projection, it's just this. You guys you already found those two pieces. Okay, so the magnitude of the projection of vector v onto vector u is just the dot product of u and v over the magnitude of u, which is 86 over root 109. I think it's started with an 8.
You can't.
2.86
I think that rings a bell.
over
86 over root 109 because it's only one magnitude, it's not squared anymore. The squared part comes from the unit vector part. But you guys get that if you did the magnitude of, or you did the square root of 568 over 109 squared plus 258 over 109 squared plus 678 over 109 squared, and then you add them up with the square root of the whole thing, you get 8.24. I actually did that the other way in the other two classes. I'm being different with you guys. Either or. Okay? There's vector projections. Okay. Now, we've got mechanical work in 3 dimensions. So if I want to do work in 3 dimensions, I just have to deal with vectors that are 3-dimensional, but it's the same formula. So if I have a force with units in newtons and defined by the force vector 300, 700, 500, acts on an object with displacement in meters defined by vector d, which is 3, 1, 12, find the work done in the direction of travel. Work done. What was the work formula again? Force dotted with displacement. Man, I wish I had vectors for those. Oh, I do. 300, 700, 500, dotted with 3, 1, 12. Apply dot product, get 900 plus 700 plus 6,000 becomes 7,600 joules. Answered. Hooray. Okay. Part B asks you, find the work done against gravity, which is a force in the direction of the negative z-axis. So whatever happened here, you guys, if there's multiple forces at work, you could technically break this force down and break the displacement down into its components. If I want just the work done that counteracts gravity, I should be focusing on what part of these two vectors? The z coordinate. So what should I do with the x and y coordinates if I just want to focus on z? Plot placeholders of 0. So the vertical components right? The z direction. Okay. So I want to do the work for just the vertical components, right? Force dotted with displacement. It's 0, 0, 5,000. Dotted with 0, 0, 12. Oh man, sorry. 0, 0, 500, dotted with 0, 0, 12, and you would get dot product 0 plus 0 plus 6,000, so 6,000 joules. So that's, you're just like focusing on one of the forces. So that's the work just going in the vertical direction, or the z direction. Cool? So you can isolate it.
And then it would be like using the y, then
Just pick the y's. You got it. Yeah. All right. The last thing, the last topic, last concept, last question you have to worry about on the assignment. There's one question. Well, there's what this concept relates to both. It's called the triple scalar product. It's a combination of dot and cross product. So now we've got a mix and match. Okay, we've got cross and dot product happening. And one such combination of the triple scalar product is vector A dotted with vector B crossed with vector C, and can only be calculated if the cross product is performed first. So typically what happens is we would put the brackets around the B cross C just to be super confirmed that would be done first. Do you guys get that order of operations? If you did A dot B first, you'd have a bit of a problem, because what's the result of the dot product? A scalar. Can you do a scalar cross vector? No. So this is where, if you go on your assignment, there was one little communication fill in the blank question, where you had to say whether or not the result of the expression was a scalar, a vector, or meaningless. Okay? Meaningless means that you're stuck with an expression that you can't evaluate because it doesn't fit the criteria, right? Like, you can only do dot product and cross product of two vectors. Okay? You can do scalar multiplication with a scalar and a vector. You can add vectors with other operations, but the cross and dot product have to be two vectors. If you want to add two vectors, they have to both be vectors. Like, there's the rules of the game, and it's basically coming up with what will the result be if you apply the rules correctly. So, this is the triple scalar product. Let's think about this. If I would have to do the cross product first, I would get a vector. But then I'd have vector A dotted with the result of that cross product, which is another vector. If I have a vector dotted with a vector, scalar results. Hence why we call it the triple scalar product. You end up with a scalar. Okay? Now, consider the vectors U, V, and W. Evaluate the expression U cross V dotted with W. Okay? So again, it's understood you're going to do that first. Okay? U cross V dotted with W equals, so we're going to have a cross product. Let's do it. Again, if it helps you, U1, U2, U3, V1, V2, V3. Okay? So cross product, I start with, just think, I always start with the band. I start with U2, okay? Start with U2. U2 is 3, V3 is 6, 3 times 6, 18, I write a minus sign. U3, V2, 1 times 5 is 5. And I'm going U3, V1, 1 times 2 is 2, minus U1, V3, 4 times 6, 24. U1, V2, 4 times 5 is 20, minus U2, V1, 3 times 2 is 6. Dotted with 10, negative 3, negative 14. So I end up with 13 dot negative 22 dot 14, I'm sorry, comma, I was in dot, 4 commas. 13 comma negative 22 comma 14 dotted with 10 negative 3 negative 14. We get 13 times 10, 130. Negative 22 times negative 3 plus 66. 14 times negative 14 minus 196. You get interesting. What does that mean? So let's think. I'm gonna get my meter sticks. Okay. I know. Meter sticks out again. Okay. So if you have two vectors that lie on a plane, I'm gonna use the board here. So you don't have to be 9-degree angles. You have two vectors on a plane, guys. Let's even just assume that the side of the poster here, my calculator poster, is one of the vectors, and there's another of the vectors. Okay, or even down here. Okay, so there's my two vectors. So we have a vector that's the edge of the poster. We have this vector. They're lying on a plane. Any two vectors will always define a plane as long as they're not scalar multiples of each other. Okay? So the cross product is a vector perpendicular to both these. It has to do this. I'm going to try not to hit Eric in the head. Okay. So does everyone get that this right here, what's poking out of the board here, this is the vector that's the cross product of u and v. Okay. So now we have just this vector. Now we have this random vector w we haven't even looked at yet. But I know that the vector w, okay, has to, if I get 0 at the end here, it means that whatever vector w is, it must be perpendicular to this. Where do you think the only place this vector could be is? Has to be on the board, because that's the only place that's perpendicular. It could be any one of these. You guys see, I was trying to talk about this in the video. It's like rotationally wise. Like you guys get all of these are 90s, because I can rotate and still be a 90 in 3 dimensions. Does that make sense? Okay, but there's no other way. Like you can't have this here and then this vector is doing this. Like that's not 90. You know what I mean? Has to be on the board to make the 90. So what this means is whenever you get that the triple scalar product is 0, means the original 3 vectors are coplanar, all on the same plane.
We'd like to make a special congratulatory announcement. Girls varsity softball team has just been crowned city champions. Congratulations, Lada, Gilligan, for coaching our team to victory. Thank you so much, girls, for an amazing effort. We are so very proud of you. Now here's the take a look.
Good afternoon, everyone. This is just a reminder that the next few days are our math PAO PLC days. Our grade 9s are reminded to be at their assigned rooms by 8:15 in the morning. Also, any students in grade 10 to 12, you're also reminded to arrive at school no earlier than 9:45 a.m. I'm sure you're going to be disappointed about that. You will not be allowed to go to the 3rd floor until 9:55 a.m. We would like to wish all of our grade 9s the best of luck over the next 2 days. And a very big thank you to the hard work of our amazing math department who have spent countless hours preparing our students. Once again, good luck.
Hi, I'm Al. I'm Alex. And we're your new publicity officer. So this is announcement, all senior and senior boys basketball players who played on the senior team must be entered on the field today or tomorrow, or 2:45. All members of the baseball team must be so at some point this week. On Wednesday and Thursday at 7, the grade 11 rap drama students are performing their one activity. It's a $2 donation at the door. Come support the drama students. That's all. And thank you for listening.
Okay, guys, I'm not saying this is the picture, but I just so you get a visual so you can write on your paper if you want. So assume that vectors u and v lie on this flat piece of paper. They're on the same plane, right? As soon as you're in a 2-dimensional land, you're on a plane. 1-dimensional land is linear land. Okay, 1 dimension is linear. 2 dimensions is a plane. Okay, flat piece of paper. You need at least 2 lines or 2 vectors to make a plane. Okay? So I have the blue plane, vectors u and v lie on the blue plane. The cross product of those is going to be red vector that's poking out of the plane, perpendicular to it. It's like poking out of it, going vertical. In order for vector W to cause the dot product to be 0, it also needs to be on the blue plane. Because what this is saying is that there's a right angle here, there's a right angle here, there's a right angle here. Make sense? It's like you're opening a page of the pages of a book, okay? Like, I don't know, all of these are all perpendicular to that one vector that's the cross product. So, I'll be honest with you, this idea right here is the, like, stepping in point to linear algebra.
Using the interruption, we have to do more analysis. Thank you. The graduating athlete list is posted inside the guidance office. Grade 12, make sure to certify your names, and if there are any problems, contact your coaches. The library club will meet this Wednesday immediately after school. Book lists are accepted for this meeting. Feel free to suggest fiction, graphic text, manga, and non-fiction purchases. This year's athletic banquet will be held on Monday, June 11th, starting at 5 p.m. Make sure to see your coaches for your tickets. That is all. Thank you.
Okay, so guys, so this is why I say this is like the intro into linear algebra, is because in linear algebra you learn about writing equations of lines and equations of planes. Okay, we leave equations of lines, like we've done equations of lines in 2 dimensions forever and ever. But you can write equations of lines and equations of planes in 3 dimensions. And it's going to be related to kind of the ideas here of how the vectors are related to how the plane is oriented. And again, I wish I could get into the next unit. And I already opened the idea that maybe on the 22nd of June, I might do an afternoon session on just linear algebra intro. If you want to come in. Okay? Pardon? Well, I could do 21st. It's like one of those end of the weekdays. Okay? Like in the morning is the exam, so we can't do it in the morning. Okay, but the building's pretty much going to be empty in the afternoon. So I would be willing to do like a 2-hour session for any students that are interested to learn about like a little bit of intro to linear algebra, what we didn't get to in Unit 8. Okay, but again, that's up to you. By the end of the week, I'll maybe have a sign-up list, and if there's enough interest, we can arrange a date that most of us are available. Okay, but for the purposes of this is all we need to know how to calculate this. What's the application of when you would do this? Oh, I'm sorry. That was a little too much buildup. Okay, so this is evaluate the dot product the other way. Compare your answer, explain why this happens. Do you guys kind of see that you're going to get the same answer because all this is a dot product, and it's commutative, right? So just so you have it filled in on your paper, we already have the vectors. Like you don't have to redo your cross product. Vector W, 10, -3, -14. Dotted with U cross V. U cross V is, we got 13, -22, 14. And we know we got 130 plus 66 minus 196. Equals 0. So compare your answer. Answers are the same because dot product is commutative. And that's all you're really doing. The cross product's it's like a piece of a puzzle, but what's the overall operation that's happening there? Dot product, you're allowed to do dot product in either order. Okay? So, one slide too early, but now I'm going to say it. The only application you have to worry about for using the triple scalar product for the purpose of your assignment, okay, is the volume of a parallelepiped. So a parallelepiped is a fun thing to say, the word of the day. Go home and use it in a sentence. Okay. So a parallelepiped is basically a 3D object that's made up of parallelograms. It's like a rectangular prism that's skewed. Okay? So, hello.
Could you come by the main office at the Belfast?
Sure.
Thank you.
Okay. Okay, so we basically know that the volume of this object would be the area of the base times the height. Okay? What I'm about to do is I'm going to go through why the formula ends up being the triple scalar product. So basically, let's go into 2 dimensions for a second. You guys see that we have vector u and vector v creating this parallelogram. Okay? Do you guys see that vector u and vector v, if I want to find the area of that parallelogram, so this is 2 dimensions, I've been 2-dimensional, right? Area of a parallelogram, if you remember, was magnitude of u times magnitude of v sine angle between. It's just normal cross product is the area of the base, because the area of a parallelogram. So that's the area of the base of the parallelogram. Right. This is the area of the parallelogram, which is the base of the parallelepiped. Okay. I know, I'm using all sorts of fun words today. So if the volume is A times H, okay, we have magnitude of U times magnitude of V sine theta, okay, times H. Okay. Now, magnitude of U times magnitude of V sine theta. That piece is the magnitude of the cross product. Part that's in the brackets is the magnitude of the cross product. So this is U cross V, magnitude. So now, I need to work with the H, okay? Is there an equivalent expression for H in the picture? So here's H, guys. H is a vertical. It goes from the top of the parallelepiped to the base perpendicularly. So it's created a right triangle here, right? There's a right triangle where that's H. This is vector W. And they've given you that the angle at the top is an alpha, just to be a different angle. So what can you think of a relation between alpha, H, and W and vector W here? Good. So cos alpha would be the H over the magnitude of W, or H is the magnitude of W cos alpha. Does that make sense? I can replace H with magnitude of W cos alpha. Is this kind of looking like dot product right now? You guys everyone kind of see this? It's basically the geometric definition of dot product where the first vector is made up of 2 vectors. But it's basically magnitude of first vector times magnitude of second vector cos alpha. So the only thing that's missing though is alpha actually the angle between these? And the answer to that is, it is. Because if I go back to the picture, please watch, guys. We all agree that H is going in the direction perpendicular to the base. Perpendicular to both vectors U and V. Isn't that exactly what the cross product's doing too? It's also going to be perpendicular to the base. So it would be like me drawing this vector, and that's vector U crossed with vector V. Take a look, guys. Z pattern. The angle between this and W is also alpha. I realize that I just lost majority of you during that little spiel, but I'm hoping that you kind of, if you go back and watch this, you kind of get the idea that what I'm trying to get at here is, and I'm not going to make you reproduce this. You don't have to prove to me that this is the volume of a parallelepiped. But this basically is dot product of first vector dotted with second vector. Now there's one other catch to make sure this is correct, because technically this could be negative. Does that make sense? This could technically be a negative answer. You get a negative value for dot products allowed, right? So how we fix that is that we put, basically we'll put it right here. We're going to put this in bars. The bars here don't mean magnitude. The bars mean absolute value, because inside there is a scalar. So basically what those do is it covers yourself. If you get a negative volume, you can't. You have to make it positive. So with my other 2 periods, I made a quick little example, and we just did it just to kind of practice. So On the back of this page, guys, it's blank.
Oh, no.
So really, really quick, on the back of, the back of this page is blank. So I'm gonna kind of, just to save time, well, I forgot some letters. Parallelepiped. Defined by U105. V2 negative 3, 1. W5, 1, 2. Okay. Made up just random vectors. Hopefully none of them are scalar multiples. Okay. There's 3 vectors. Find the volume. So parallelepipeds defined by these 2 vectors. Start at one point, draw a vector, draw a vector, draw a vector, connect them all up with parallel vectors, and you get a parallelepiped. Okay? So find volume. Volume would equal U cross V dotted with W. You cross product the first 2, dot it with the third, you're going to get a number, and that number will be the volume. And to cover yourself, we're going to put it in bars. Yeah.
Why'd you get rid of the cos? Like, for example, when you just said cos alpha when you took out the x.
Because I turned it into dot product. So I used the geometric definition of dot product and rewrote it in terms of its original form. You see magnitude of first vector, magnitude of second vector, cos angle. You can just say, oh, well, that's the dot product of the first 2. Okay? Now, we're down to 2 minutes left, guys. So shall we say you're going to figure this out by yourself, or you guys want to quickly do it, like in the next 90 seconds? Okay, I'm just going to do it. Then it's done. Okay, so vector U, cross V, 0 plus 15, comma, 10 minus 1, and then negative 3 minus 0, dotted with 5, 1, 2, equals 15, 9, negative 3, dotted with 5, 1, 2, is 75 plus 9 minus 6. 78? So, if you did all that, if you had gone a negative in there, the bars would have made your volume the correct sign. So that's why we have the bars. So what have you just found? Defined by 3 vectors, you just found the volume of that parallelepiped. So you should be able to do number 10 now of those assignments. Assignments due tomorrow. Have fun tonight. Do your own work. Don't copy each other. Okay? And I will see you tomorrow as we begin the exam review fun.